somebody doesn't have to grade the same assignment twice, right? So you make a decision among yourself who's going to submit. Okay, so let's see. Let me see if I can explain this. I'm hoping that's big enough, or maybe I should make it even bigger. Maybe bigger. That should be big enough. Okay. So it says you can skip until the main function below. So we'll just skip the main function below. So what it ends up doing is maybe I'll just talk about this later, after you've had a chance to look through the assignment and the vulnerable program once yourself. Otherwise, I may be trying to give you details that you're not ready to look at. So I'll do that in the next lecture, okay? Make sure that you go through the assignment carefully before that, okay? And again, there's always a possibility that the quiz may include, what is in that handout, okay? So it's not, if there is a quiz on this, then I can ask you all kinds of detailed information on the write-up, but I don't necessarily expect you to know how to do the assignment at this point, right? So the goal is, if I have a quiz, the goal is to make sure that you read this very carefully now, rather than waiting until next week or something like that, because you will find that when you start, you are going to be lost, okay? So you really have to read it carefully and then come to the class, and so that you are ready to understand what I'm going to be able to tell you at that point, right? Because if you haven't read the material, then nothing I tell you in class will make any sense. So make sure that you read it carefully, and then you'll be able to go from there. Okay, so with that I'll stop the discussion of the assignment and get back to our quickly finish up this topic of memory corruption and low-level exploits in C and machine code. Okay. So, in the last lecture, we talked about various ways to deal with these memory errors, and where the approach that we spend most time on is exploit mitigation. How do you make sure that the exploits don't work? But there is, of course, an even better approach of making sure that the memory errors themselves don't happen. Okay, so that's what we are going to talk about today. But we are not going to look at it in a great level of detail because techniques for detecting and preventing all memory errors generally tend to impose both a compatibility cost and also a performance cost. Right? So compatibility cost in the sense that programs that used to work before no longer work, and the performance cost, of course, things become slower. So, but still, the discussion won't be complete unless we have an understanding of the problems themselves and how one could get rid of them once for all. Okay, so there are two types of memory errors that we have mentioned before. Spatial error means you allocate an object of a certain size, and then you try to access something outside of that size. So here we are allocating an object of size 10 bytes, and then you are accessing something that's 15 bytes. Obviously, that will be outside. The temporal error is one where you allocate it, and it has been, and you free it, but still you access it after freeing. Right? So you have a pointer free. You have freed that. That means P is no longer valid. It's pointing to some invalid memory region, and then you go ahead and access it anyway. Okay? And when you do that, it's possible that it points to something that's still free, in which case the damage is somewhat limited. But if it is, but it's more likely that the object may have been reallocated, because the way heap management routines are written is that the heap management, one of the issues is whether to ensure that there is locality. Okay? So locality means you want to make sure that the most recently used object is again used again. That way, things will be in the cache, or if you're talking about virtual memory, then they'll be in main memory rather than on the disk. So because of that, most memory management routines or heap management routines end up, aggressively reallocating data that is free, and therefore, if you access an object after it is freed, chances are that you are accessing some other object because the memory has been allocated to something else. Okay, and so these are the two types of errors, and there are various techniques to detect these errors. And the problem is, there is a lot of C code that exists, right? I started looking at some of the source code of these utility programs in the 80s, and I can. It seems to me that some of the programs haven't changed since then. Okay, so you can imagine that if we are carrying around programs from so long ago with maybe minor updates or no updates at all, then compatibility is a real issue, right? Because there's tons and tons of C code that we can just, that was written 10, 20, 30 years ago, and we are still using it. And so if somebody says, this feature that you used to rely on in C will no longer work, that's not a workable thing, because nobody has the capacity to rewrite all of this code. So the question always has been, okay, how can you find all the memory errors without breaking any existing code? And this is a difficult challenge, because in C there are all kinds of features like pointer arithmetic, conversion between integers and pointers. You have unions and casts and all kinds of features that really make it very difficult to figure out whether something is a pointer or not. Okay, so as you can see, there are conversions between integers and pointers. So if you want to track pointer errors, but you don't even know whether something is a pointer or an integer, you can see how hopeless the whole thing seems. The second type of compatibility issue arises, and then you may not immediately recognize it, and that has to do with the fact that there are already some compiled libraries, and you're going to link those libraries with your code. Even if you compile your code to use pointers in a same way, the libraries may not, cooperate, and so the problem that you often get into is that any technique for protecting pointers ends up having this kind of cross-component dependencies and interactions, and as such, they are hard to deploy. So the compatibility issue is not just that any particular program breaks, but the interface between the program and the libraries that it uses, they break, and that's okay. So so of course we could all use safe languages or supposedly safe languages like Java, right? And so in Java, right, there is no spatial error, right? So how do you avoid a spatial error in Java?
No point.
If somebody can lift their hand and speak loudly, then yeah, go ahead. And what does it do? So that is true, but can you be more specific as to why, right? I mean, in C, it's not, while you can access and print out the value of a pointer, it's not that is not the feature that causes problems. Right, so pointer arithmetic. And is it true that there is no pointer arithmetic in Java?
Not the way it is in C.
Right, so in particular, the basis of much pointer arithmetic is array subscripting, right? And in C and C++, the programmer is supposed to know whether they are accessing a subscript within the array or whether it goes beyond the end. In Java, the subscript check is done by the language, and it's always present at runtime, and therefore you can never go outside the array. And it doesn't have any other type of general pointer arithmetic. The only pointer arithmetic that kind of implicitly happens is the array subscripting, and that's very easy to check. Okay? So how do you avoid temporal errors in Java? Somebody else? Yeah. So there is no explicit free. So there is no chance that you could, free the data and then use it again, right? If you have a pointer to some data, then it's not going to be free. Okay, so there is no way to, free something else. So people have definitely looked at using garbage collection in C, but there is this fundamental problem that in C is not a type-safe language, and therefore you don't know whether something is a pointer or not. Okay? So if you don't know whether something is a pointer, then what can you do? Because I have some variable. If it is a pointer, then it is pointing to some memory block. But if it's an integer, then obviously it's doesn't mean anything, right? So if you want to do any kind of garbage collection, you run into this problem that you don't even know what are the pointers that this program has. So I cannot figure out what is garbage. So by the way, what is the definition of garbage? Yeah.
The data that have no reference, like no variable is pointing to it. So
Correct. So garbage simply means you have the program has no pointers pointing to that memory block. Okay? And so naturally, well, given the definition, it's immediately obvious that in a C or C++ program, you cannot figure out whether something is garbage or not. And therefore, garbage collection is not a realistic option. That didn't prevent people from trying, and so basically, there is a technique called conservative garbage collection that people have tried to implement for C and C++, and it works reasonably. But what happens is that there are going to be corner cases where the system cannot figure out whether something is garbage or not, and therefore it will not be able to free that memory, and so that contributes to essentially a memory leak, right? So the garbage collector cannot do a perfect job in C or C++. It can do something, okay? But a lot of people, a lot of programmers in C and C++, they swear by, not using garbage collection, right? So they say, I'm using C because, I can deal with, memory management. Which is of course not, right? None of us is, memory management, manual memory management is an extremely hard problem. It's not that it cannot be done. If you think about garbage collection, think about memory management right from the beginning of the time when you design your code, then you can design it in such a way that memory management is easy. But most of the time we don't do that. We just go ahead and write some code. We have some mallocs here and freeze there, and later on we want to we realize that okay, we can't we realize first that there are memory leaks in our program, and then we say okay, let me find those memory leaks and free the data, and then we realize that if we free them, then we run into temporal errors. And essentially what happens is that many times the program is written in such a way that you cannot figure out whether at some point you're ready to free the object or not, because you didn't think about it right from the beginning, so you didn't design it in your code, and so you just don't know whether something should be freed or not, and essentially as a result you basically end up tolerating a lot of memory leaks. So living without garbage collection is certainly a big problem, but that is the world most C and C++ programmers live in, and that is also the reason why many of these memory errors just don't go away, and the vulnerabilities have been there for 20, 30 years, and they're not going away anywhere. Right? And also, people thought, okay, we'll use safe language, do everything in Java, and then problems will go away. What happened was that even through Java, there are these native methods and native interfaces. Right? Those are low-level interfaces, and Java programs can use those native methods, and those native methods are often vulnerable, and so what can happen is that attackers can use a Java function. The Java function uses a native method, right? And the data gets passed from the Java function to the native method, and now the native method, the vulnerabilities can be exploited directly from Java, right? The situation was so bad that I don't remember how many years ago, maybe it was within the last 10 years, right? So people were advised, don't use Java anymore, because the situation is so bad that you should just stop using Java for anything that has any potential security impact. Okay? The situation is presumably not as bad anymore, but it was certainly very bad at some point. Yeah.
What exactly is like a native method? How exactly do you?
So native method is just think of it as, the system, suppose, so Java programs, right, when they do input output, they simply go to the operating system to do the input output, right? So those methods will be, their implementation will be in C and compile to assembly and so on, right? So Java programs are simply passing on. So basically Java program is just a layer in between, right? So the underlying machine is always doing, assembly, right? So anytime those interfaces would be needed. Okay, so there are three broad approaches for detecting memory errors. The first two are only dealing with spatial errors, right? So both of these techniques are dealing with spatial errors, whereas if you the third class of techniques can look at can deal with both spatial errors and temporal errors. Okay, I'm just going to give you a quick idea of what's going on. So the simplest approach is what is called the red zone approach. Okay, so the idea is very simple. For each object, you're going to leave some gap on either side of the object. Okay, this gap is called the red zone because you're not supposed to access it. Right? So any pointer, if it goes out of bounds, chances are that it's going to be pointing to this red zone, and if you have some way of checking whether any pointer is pointing to your red zone, that allows you to identify some of these spatial errors. Okay? So there are many tools and research papers. So Address Sanitizer is a tool that is widely available, and it uses this red zones to protect. I forget whether it protects stack data or not. It certainly protects all the heap data using red zones. You can certainly protect stack data. There is nothing. A tool that operates at the compiler level, which is what pretty much all of these tools they are. They are typically implemented as part of a compiler. Okay, so they look at the source code and they operate at the source code level. And when you operate at the source code level, it's possible to put padding around variables on the stack as well as variables that get allocated in the heap. Okay, and then whenever something is accessed, you can check whether it's pointing to the red zone or not. Okay, so the point is that what you can do is before you dereference a pointer, you can check is it pointing to a red zone. If it's pointing to a red zone, then you're going to announce an error and maybe abort the program. So how many of you have used Valgrind? Okay, so if you are a C programmer and C or C++ programmer and you haven't used Valgrind, then there's something wrong with you.